Magnetic induction is one of the most important concepts in the electrical field. It is the basic operating principle underlying alternators, transformers, and most alternating current motors. It is imperative that anyone desiring to work in the electrical field have an understanding of the principles involved in magnetic induction. The principle of magnetic induction states that whenever a conductor cuts through magnetic lines of flux, a voltage is induced into the conductor, a magnetic field is created around the conductor. The direction of the current flow determines the polarity of the magnetic field, and the amount of current determines the strength of the magnetic field. That basic law in reverse is the principle of magnetic induction, which states that whenever a conductor cuts through magnetic lines of flux, a voltage is induced into the conductor. When the conductor is moved downward through the magnetic lines of flux, the induced voltage will cause electrons to flow in the direction indicated by the arrows. This flow of electrons causes the pointer of the meter to be deflected from the center zero position. If the conductor is moved upward, the polarity of induced voltage will be reversed, and the current will flow in the opposite direction. The gauge will be deflected in the opposite direction. The polarity of the induced voltage can also be changed by reversing the polarity of the magnetic field. Fleming's left-hand generator rule. Fleming's left-hand generator rule can be used to determine the relationship of the motion of the conductor in a magnetic field to the direction of the induced current. To use the left-hand rule, place the thumb, forefinger, and center finger at right angles of each other. The forefinger points in the direction of the field flux. Assuming that the magnetic lines of force are in the direction of north to south, the thumb points in the direction of thrust, or movement of the conductor, and the center finger shows the direction of the current induced into the armature. An easy method of remembering which finger represents which quantity is shown below. Thumb equals thrust, forefinger equals flux, center finger equals current. The left-hand rule can be used to clearly illustrate that if the polarity of the magnetic field is charged or if the direction of armature rotation is changed, the direction of induced current will change. Also, moving magnetic fields. The important factors concerning magnetic induction are a conductor, a magnetic field, and relative motion. In practice, it is often desirable to move the magnet instead of the conductor. Most alternating current generators or alternators operate on this principle, determining the amount of induced voltage. Three factors determine the amount of voltage that will be induced in a conductor. First, the number of turns of wire. Second, the strength of the magnetic field, flux density. And third, the speed of the cutting action. In order to induce 1 volt in a conductor, the conductor must cut 100 million lines of magnetic flux in 1 second. In magnetic measurement, 100 million lines of flux equals to 1 Weber. Therefore, if a conductor cuts magnetic lines of flux at a rate of 1 Weber per second, a voltage of 1 volt will be induced. Lenz's law. When voltage is induced in a coil and there is a complete circuit, current will flow through the coil. When current flows through the coil, a magnetic field is created around the coil. This magnetic field develops a polarity opposite that of the moving magnet. The magnetic field developed by the induced current acts to attract the moving magnet and pulls it back inside the coil. If the direction of motion is reversed, the polarity of the induced current is reversed, and the magnetic field created by the induced current again opposes the motion of the magnet. This principle was first noticed by Heinrich Lenz many years ago and is summarized in Lenz's law, which states that an induced voltage or current opposes the motion that causes it. From this basic principle, other laws concerning inductors have been developed. One is that inductors always oppose a change of current rise time of current in an inductor. When a resistive load is suddenly connected to a source of direct current, the current will instantly rise to its maximum value. The induced voltage is proportional to the rate of change of current, or the speed of the cutting action. The exponential curve. The exponential curve describes a rate of certain occurrences. The curve is divided into 5 time constants. Each time constant is equal to 63.2% of some value. An exponential curve can be seen if graphed. The exponential curve can often be found in nature. If clothes are hung on a line to dry, they will dry at an exponential rate. Inductance. Inductance is measured in units called the Henry and is represented by the letter L. A coil has an inductance of 1 Henry when current change of 1 ampere per second results in an induced voltage of 1 volt. The amount of inductance a coil will have is determined by its physical properties and construction. A coil wood on a non-magnetic core material such as wood or plastic is referred to as an air core inductor. If the coil is wound on a core made of magnetics such as silicon steel or soft iron, it is referred to as an iron core inductor. Iron core inductors produce more inductance with fewer turns than air core inductors because of the good magnetic path provided by the core material. Iron core inductors cannot be used for high-frequency applications, however, because of eddy current loss and hysteresis loss in the core material. Another factor that determines inductance is how far the windings are separated from each other. If the turns of wire are far apart, they will have less inductance than turns wound closer together. The inductance can be calculated as follows. The formula indicates that the inductance is proportional to the number of turns of wire, the type of core material used, and the cross-sectional area of the core, but inversely proportional to core length. An inductor is basically an electromagnet. The same factors that affect magnets affect inductors. The permeability of the core material is just as important to an inductor as it is to any other electromagnet. Flux lines pass through a core material with a high permeability, such as silicon, steel, or soft iron, better than through material with a low permeability such as brass, copper, or aluminum. Once the core material has become saturated, however, the permeability value becomes approximately 1 and increase in turns of wire has only a small effect on the value of inductance or L time constants. The time necessary for current in an inductor to reach its full Ohm's law value is called the L time constant. Can be used using the formula above. T equals L or induced ED voltage spikes. A voltage spike occurs when the current flow through an inductor stops, and the current decreases at an exponential rate also, as long as a complete circuit exists when the power is interrupted. There is little or no problem. Thank you for watching, and please like, share, and subscribe.